Hello and welcome back to High Peak Education. I would like to perform a video which has us examine rotational kinematics, in particular for a rotating turntable. So in other words, multiple point objects, that is multiple particles, at different radii. So let's let this ladybug and this beetle be our point particles. If I show the ruler, I think the ladybug is at a location of 2 meters from the axis of rotation. And then the outside of the turntable here is going to be 4 meters from the axis of rotation, which is where the beetle will be located. Because this is a turntable that is free to spin on its own, it should spin about its own axis of rotation, being the center of mass. Because it's not constrained to have an axis, an object in solid body rotation should spin around its own axis of rotation, being its center of mass. Okay. So what we'll also show is we'll show the velocity vector and the acceleration vector. Now you'll see the velocity vector will be tangent to the path of each of these bugs, and that will be tangent to the circular path, whereas the acceleration vector should be centripetal. It should be inward towards this axis of rotation when they're in uniform circular motion, but when we're not in uniform circular motion, when we're speeding up, we should have the axis of rotation vector, but when the rate of rotation is increasing, there will be a tangential component to the acceleration, not only a centripetal component. So let's try to speed up this turntable. I'll try to do this as carefully as I can, so watch closely. Okay, hopefully you saw that the velocities are tangent to the path and the accelerations are centripetal. How about if I try to speed this rate of rotation up all the more? Hopefully you saw the acceleration vectors were tangential for a moment while I was speeding up the rate of rotation, but now they're centripetal only and the velocities are tangent. Okay, so I'll pause because I think looking at that turntable can make you feel a little dizzy. So let's be a little more quantitative when we examine this. So let's go over to the version where we can plot the position, the velocity, and the acceleration. But I'd like to plot the angular position, the angular velocity, and the angular acceleration as a function of time. So now with the aid of our graphs here, that is theta, omega, and alpha, that is angular position, angular velocity, and angular acceleration, we've set them to be units of radians for angle theta, radians per second for angular velocity omega, and then radians per second squared for angular acceleration alpha. With those in mind, let's see what happens if we have a constant angular acceleration, or at least roughly, to each of these quantities, and then we'll allow these beetles to go in uniform circular motion. So now let's try to examine using position versus time, angle versus time, and angular acceleration versus time graphs what a constant angular acceleration should roughly look like. So I'll do my best. This is actually very hard to do on this turntable, but I'll start the time, and notice that the position, the velocity, and the acceleration, that is the angular position, angular velocity, angular acceleration, are just constant with time. And let's go ahead and see what a roughly constant angular acceleration looks like. So hopefully you saw that something interesting happened there. Okay, so let's stop and take a look at the graphs here. So notice that we have that the position went up very rapidly as a function of time, and then it is roughly constant as a function of time. Okay, so there we go. So notice that at this uniform circular motion, the position continues to go up as a function of time. The angular velocity is now constant as a function of time in uniform circular motion. But previously, when there was that angular acceleration, the angular velocity went up, and notice I'm changing the scale here very substantially. It went up quite rapidly. So there was a sudden increase in the angular velocity, but then we quickly also slowed it back down. So then we arrived at roughly a smaller angular velocity. The angular acceleration is now 0 in uniform circular motion. But you'll notice that during the time period that we increased the rate of rotation, it was quite sudden and it was quite large, and then the period of time where we decreased the rate of rotation. So you'll want to go back to the video and take a look at that. Okay, so this is what it means to have an angular acceleration, an angular velocity, and an angular position. Alpha, omega, and theta. So I hope this video was helpful. Thank you for watching this video. If you like this content, please smash that like button, and please subscribe to the channel to grow the channel. Please share this amongst your social network, and I will see you in the next video.